Good morning, everyone. I'm Ye Wang. I'm from the University of Melbourne. Today, I'm going to present this work. The title is Path Following by Formations of Agents with Collision Avoidance Guarantees using Distributed Model Predictive Control. And this work has been done with Yujia Yang, Dr. Ye Pu, and Professor Chris Manzi. And my talk have the following 5 parts. First, I will start with the introduction to this work. And in the second part, I will present some preliminary results that have been used in this work. And in the third part is the main result for this work, that is a distributed MPC formulation. And in the fourth part, I will show you some simulation results. Finally, I will give some conclusions. Let's start from the introduction. In this work, we would like to develop a tractable distributed MPC formulation for autonomous vehicles. So in our lab, we have several autonomous ground vehicles, and also we also have 2 these USVs. And we would like to operate these robots to complete a task with multiple objectives, including path following, formation, and collision avoidance to both static and dynamic obstacles. So in the preliminaries, first we consider a class of multi-agent systems, including in total M agents. And for each agent I, it can be modeled by the linear time invariant dynamics. And for this multi-agent system, we also consider it follows a fixed and directed graph, which means any 2 agents inside can communicate with each other bidirectionally. And the second result we have used is a centralized MPC full tracking framework, and this tracking MPC basically from this reference from Professor Limon's group, and so the reference is given as this YT is a piecewise constant reference, and in this in the constraint there is a optimizable output can be generated from the study model that is denoted by YS tilde. And in this tracking framework, the admissible output is going to track the given reference. So the main advantage of this work is the MPC is always feasible. So then we would like to extend this MPC into the distributed case. And the last result we have used is this mixed integer programming formulation. And this is from this reference from Professor Sorin Olaru. And this formulation will be used in the collision avoidance constraints. And let's consider a polytope. The set S is defined in the half-space representation. And this set S is in the real space and could be bounded by another set X. And then we can find the complement of this set S is defined by the CXS. And note that X can be also considered as the entire real space. So then the complement of these sets can be denoted by the CS. And this complement set is a non-convex set, and it can be reformulated by a union of a partition space. And then a tractable problem formulation for this complement set can be formulated by using the mixed integer programming as denoted here. So there exists a very big scalar, gamma, to violate the constraint, and with the binary variables, so alpha I. So for each linear constraint, define this set S can be violated with the choice of the binary variable. Then in total, the sum of this alpha L should be less or equal than the number of the linear constraint minus 1. And in the main result, since we have three objectives, so first we consider the distributed MPC formulation is under a leader-follower structure. So to do the path following, so we mainly set the leader follows a path supplied from a given path planner. And for the formation, we can find the position for any two agents, agent I and agent J. So the leader and the follower attempt to maintain a desired formation, which is defined by this vector dij bar, and the position pi minus bj should track this desired formation. For the collision avoidance, we consider any agent does not collide with static or dynamic obstacles. So for the dynamic obstacles, also including the agent, so the other agents. So mathematically, these two cases can be formulated as follows. So for the static obstacle is defined in a set as Sj, and the position for any agent I, the agent should not be inside this set. And for the dynamic obstacles, we consider for each agent there's a set as is defined by St around this the center pi, and for agent I. Also, there's another set for the agent J. So if these two agents do not collide with each other, which means these two sets, the intersection of these two sets is empty. So since the formation and the collision avoidance, those formulation we cannot use directly. So then we just reformulate to be tractable in the distributed MPC formulation. So first, we start from the formation. We introduce the relative distance vector as a new state, and to update just replace the position of this agent, and then we can define a new state vector, including the relative distance and also the velocity in the x and y axis. And then with this new updated model, we can reformulate the formation cost function. So which means the relative distance will directly track the desired formation vector dij bar. So note that here the dij could be also time varying, and it can be updated by using this formulation with a rotation matrix is defined by this r bar theta. And the theta actually is a desired angle between any two agents. And from the heading angle of the leader is denoted by the ThA1. So we can rotate the desired formation vector for each time step. And for the collision avoidance, and for the we have two cases. First one is a static obstacle. So as I mentioned before, the position of agent I should not be inside the static obstacle in order to avoid the collision. So which means, and it is equivalent to the pi is in the complement of this set. And then we use the mixed integer programming formulation, and we can just reformulate this condition using the similar technique as stated here. And for the dynamic obstacle, similarly, instead of using the position, we use the relative distance. So the vector is denoted by the dij, and we can reformulate the condition for this collision avoidance to the dynamic obstacle. And so we can see the variable become the dij. And then we also use this mixed integer formulation and to find this collision avoidance constraint. Then in the total cost function, we follow the centralized MPC for tracking framework, and we just reformulate for each agent I. And then we could find this one, and then in total we have this distributed MPC optimal problem with the total cost function. We have the collision avoidance constraint as described before. We also have the prediction model, and with the study model to generate the measurable output for each agent. And we also have the terminal equality constraint. So for the simulation result, here we provide a video we can show you later on. And in summary, that we want to operate 3 ground vehicles to track a given path around the static obstacles. And for any 2 agents, we also, for these 3 agents, we also want to form a triangle with a distance equal to 2. So here from the similar result, we can see, so any 2 agents cannot collide with each other, and also the desired position is can be reached, and also we have this constraint for the input. So as a conclusion, here in this work, we develop a distributed MPC formulation for path formation and collision avoidance. We consider the path is supplied by existing path planner, and will provide some simulation result. Currently, we are working on the analysis of the closed loop properties. And also we are investigating is there any additional condition required for the planned path. And also we are working on the experiment with the real robot. So that's all. Thank you for your attention.